Connected vehicles and their services are in everyone's near future. All of these services will require a much larger data transfer capacity from the vehicles to the cloud than what is available today. The AECC is dedicated to helping address the data transfer requirements of this growing ecosystem. Our Proof of Concept, or POC committee, is focused on developing technology demonstrations that bring these services to life. Let's take a closer look at some of our existing POC demos. Conducted by Denso, KDDI, and Toyota, this AECC Proof of Concept demonstration simulated how to address network congestion for connected vehicles using an HD mapping application within an urban LTE environment. Global deployments of connected vehicles can climb to hundreds of millions and eventually billions of users, which makes the traditional mindset of throwing bandwidth at it to resolve network congestion simply too expensive and impractical to scale. Using existing network resources, AECC's low-cost, distributed edge computing approach, known as opportunistic data transfer, or ODT, enables network operators to reduce network congestion for a growing spectrum of mobile services. For connected vehicle services to work, mobile network operators need to solve the challenge of network congestion using network data optimization. This means that as vehicles and global fleets move through cities where there is a high demand for network support, they need to determine which data to prioritize. Vehicles will also travel through rural areas where there are vastly different connectivity situations and coverage on different corresponding networks. ODT helps prioritize data, moving low-priority data to off-peak hours, avoiding congestion that could disrupt critical connected services during peak hours. The results demonstrated that the AECC ODT framework is effective at optimizing the high volume of HD mapping data during peak and non-peak hours using existing network resources. To learn more and get involved, visit aecc.org/proof-of-concepts. This AECC Proof of Concept, conducted by Oracle Japan, sought to confirm the AECC's approach to enabling data integration of distributed edge computing for HD mapping and prove it as an affordable solution for HD map data. HD maps are a primary use case for connected vehicles. These maps consolidate static and dynamic information, such as the vehicle's position and its relationship to other vehicles, pedestrians, and obstacles, to help ensure the accurate, safe operation of connected vehicles. But creating and distributing an HD map in hundreds of millions of connected vehicles is a massive challenge. Multiple global and regional stakeholders require many data transactions with high capacity and efficient processing to keep HD maps up to date. Legacy systems are unable to perform these requirements on a global scale. This study simulated the AECC's concept of data offloading at distributed edge computing locations and tested the accessibility of this data. It also included the AECC's concept of edge server selection, which ensures that data is distributed and processing occurs at the server where the data resides. The results verified that AECC's approach to data integration enabled interoperability with multiple clouds and up to a 10 times reduction in query latency using a subquery component. The study also determined the optimal driving route for each vehicle, considering factors such as road width and traffic congestion, with an average processing time of less than 200 milliseconds. This POC, conducted by KDDI Corporation, Nexar Incorporated, and Oracle Japan, demonstrates how connected vehicle geolocation services, powered by AECC's hierarchical architecture approach, can reliably find free street parking spaces in a city's busy business district. The search for parking spots is a significant source of wasted fuel in urban areas, and it also contributes to congestion on the street. This POC sought to address that issue and deliver real-world benefits for the average driver. To keep costs low, the POC used regular cars, standard dash cameras, 5G network connectivity through 2 existing edge networks, and a standard commercial cloud service for vision AI-based processing and data analytics. The test not only verified AECC's concept for scaling mobility services using existing edge and cloud infrastructure, but also showed that the communication path between a car and edge clouds can be dynamically switched without interruption based on a moving car's location. The POC was able to reduce locally produced data and minimize unnecessary transmission of that data to and from the cloud data centers, delivering them right back to connected vehicles. Plus, AECC's scalable distributed edge computing approach enabled the POC to bypass the challenge of centralizing geolocation data from millions of other vehicles on the road. The AECC architecture also eliminated dependencies on specific providers within each cloud, edge access network, and services domain. Tests confirmed the ability of the service to accurately detect free street parking spaces. Additionally, it proved that distributed processing did not confuse the vehicles. Test vehicles were in continuous motion, transmitting geospatial data to two different edge networks for local pre-processing, then onto central cloud servers, then back to the vehicles. The service operated continuously and protected the privacy of each car's data. And finally, the test also proved vision AI technology can scale to process uploads from many vehicles at the same time, enabling a reliable parking spot detection service for commercial deployment. To learn more about this proof of concept and to get involved, visit aecc.org/proof-of-concepts.